Okay, we'll have our next speaker, Saeed Al-Halaj, and he'll be talking about net energy, thermal energy storage.
And thank you for braving Friday morning. I think everybody's asleep or somewhere else having fun. So my presentation is about, you guys probably heard about battery storage, thermal storage. And mainly it's used for demand shift or something that you store and then use later. In this case, we're going to look at it a little bit different. The main motivation, and if you're paying attention, the biggest problem that we have right now is actually peak demands. And that is basically because of many reasons, whether it's renewable energy penetration that adds to the duck curve. You have morning and evening ramps up and ramps down. Or for peak demand, you see now utilities are opting out for different structural pricing. You have on-peak, off-peak, but you also have something called demand charge, which actually for commercial buildings, this is the biggest penalty they pay. In areas with high demand, such as California, Texas, actually more than half of their bill is actually for demand charge. You guys know what demand charge? Anybody here? Okay, so demand charge, basically, when you consume electricity, let's say in California, you pay, if you're at night, you pay low price, which you know, which is price. Sometimes at night is 5 cents, during the day, 20, 30 cents. That's known. But the big one is they cap you at a certain power. So if you say your power is, as a building, is 100 kilowatts. So if you consume below 100 kilowatt any time of the month, you're okay. The minute you hit above 100 kilowatt, even for just 15 minutes, they charge you $15 per kilowatt. This is power charge, not energy charge, and they run it for the whole month. So it's like a penalty, so you don't exceed your allowed maximum power. And that's actually now, that's the trend that utilities are using to encourage people not to use high power during peak demands because it costs them to build inefficient power plants or building extra infrastructure. And that's what you see a lot of the motivation in California, New York, and Texas. Does that make sense? So our goal is not to actually shift from day to night where it's cheap versus. Our goal is how can I dampen that peak? That curve is sharp. If I can lower it, I can save half of the bill, which is completely disproportional on the dollar-wise. Does that make sense? So what we're doing is actually look at the whole country, and we found that the biggest consumer in commercial buildings are actually what's called rooftop units. These are air-conditioned. When you walk into McDonald's or a bank or any of those Walgreens big boxes, you see those are all air-conditioned with what's called rooftop units. Those rooftop units are actually the biggest consumer of electricity, especially during daytime, and you hear a lot about that. If you're at home, you have the option to, the utilities say, why don't you increase the temperature? At those buildings, they can. They cannot. The customer expects to go in and have fun and they want to cool, they cannot change it, and that's what's happening. So what we came up with a solution, actually a thermal energy solution, which combined wax, which is like ice. When it melts, it has a ton of thermal energy or latent heat, with graphite. The reason is because wax, it has a lot of latent heat, but it's a terrible heat conductor. So overcome that, we can infuse it with graphite, expanded graphite, and that moves the thermal conductivity actually by an order or 2 orders of magnitude, bringing it more to metal. That is important because our goal, if you're trying to move energy in and out fast, that means your kinetics has to be fast. You cannot wait 6 hours. You have to do it within 15 minutes, 30 minutes, 1 hour, because that's how you're compensated. That's how you're paid. And that is similar to the hybrid car. Probably you guys seen that the hybrid cars came 20 years ago. They're now about 5% of the world because it's much easier to have a hybrid car than a complete electric car. In a complete electric car, you need energy to drive for 300 miles, which is the biggest challenge today, is how can I put energy storage? In a hybrid car, you get the best of 2 worlds. You get an internal combustion. So the Prius actually, for that mid-sized vehicle, you need a 2-liter engine. But if you change the drivetrain from mechanical to electrical and augmented with a battery, then you can operate the combustion engine and it's always at optimum. Anybody has a hybrid? Nobody? So if you run a hybrid, you see the engine always running at the optimum RPM. And then if there's extra power, it's stored in the battery. And when you want to accelerate, The engine still has the same power, but that extra power is coming from the battery to push and compensate. So what you do with that is you actually keep operating at the best efficiency. If we can do the same with air conditioning, which means we can do the same by having, instead of a 5-ton, we can do the same load with 3-ton and optimum. And when at night, when there's extra, when there's low air conditioning need, you can charge your thermal battery. And during the day, you don't run it up and down, which is very inefficient. You just let the thermal battery add that cool to cool the air. Is that all right? So basically, you're optimizing the performance of the system by augmenting it with a high kinetics energy storage. Why is that critical? Because then there's two things here that are critical. Unlike other storage system like ice, I can then pick the material, the polymer or the wax, to match the compressor temperature. So I don't need to add another chiller or another compressor. I can just do a simple manifolding at night to charge my battery. And during the day, when I need the energy, I can just switch it through control, and the batteries then start adding load because I operate the same temperature. And that is critical because the last thing you want to do is to tell the OEM what, add this or that. You want to do it at a cost that is competitive, and you don't want to add too many parts. Just make it very simple, in and out. And I think that is where actually we got a lot of our IP is around integration by downsizing the chiller or the compressor and actually improving the efficiency. So why is that critical? Because what you see here, all we do, we take a secondary liquid and run it through those slabs. Those slab has storage material and graphite, so it's kinetic. I can move it very fast and very slow, and I can optimize the material for energy and power. So now I have flexible material that can run with any OEM's air conditioning system. We built a 1-ton-hour unit. We tested it. We published this work, but just to show you the way it works when the fluid comes from the top. So at night it's cold. When you see the fluid, the temperature start going down, which means those are melting. And this is the bottom here where you have still cold till you finish it and get all the thermal energy out. I can do this in an hour, 2 hours, and I can do it in 15 minutes. Instead of putting the fluid from one side, the top down, I can split it as a heat exchanger and get it outside. So that gives me a lot of flexibility, and that allows me actually, if you look at compared the actual AC versus a system with our thermal storage, we improve efficiency by 15 to 20%. I don't know if you guys know, but the air conditioning industry tried for years. They tried to improve efficiency. They went up by a few percent by using what's called variable speed versus 1-stage, 2-stage. By adding this thermal storage, we just were able to do it in double figures. And that is not surprising. Anybody who knows about the hybrid actually, miles per gallon is twice the conventional car, because when you stop and go, you don't run the combustion and waste fuel. And that's exactly what we did here. We can give you the same load with half the compressor size with high efficiency. And that means you can also save money, but also save emission. And that is critical because what we found, one of the reasons for that thermodynamically, when you make cold air during the day, it's hot. The compressor is operating maximum efficiency. It's inefficient and it's highly contaminating from an environmental viewpoint. When you do it at night, you run the RPM and the air is cold. So thermodynamically, you need less work to cool that air. And that was the actual work that we did. We work with Department of Energy, National Renewable Energy Lab. We've been working with them for 3 years. And one of the things we did, we took the model of the system with the prototype, and we had them simulated across the country. And we were able, especially in areas with high power demand, to cut load by 30% or 2 kilowatt. If you're in California or New York, your system will get subsidy that basically makes it free. That's how much they're desperate for energy efficiency. They pay for that because utilities are struggling to add capacity and upgrade the infrastructure. So actually, if you have a system that can shave the peak by 2-3 kilowatt, they pay you thousands of dollars because you save them building those peaker plants or even adding infrastructure. It's also for the building owners. You save money, high efficiency, and now you probably hear about net zero energy worldwide, carbon footprint and all that. So this way, we're not changing anything in the way they buy those systems or operate. We're just making it more efficient. There's a lot of talk about compared with lithium batteries. Lithium batteries are great. I work in lithium batteries, but they have limited life, they're expensive, and also they are electric. Most of the load you need, we found 50-70% in peak demand are actually cooling and heating. So why do you make electric and then you lose by efficiency around efficiency and add the electric component? You can do it direct thermal. There is ice, which as I mentioned to you, it's a problem because you can only do ice for 6 or 8 hours. It's very hard to move heat in and out. That's why they have the igloo. And then you have wax, which is only the wax, which is, it's okay, but it has very little thermal conductivity, which means you cannot move heat in and out. And finally, you have the variable speed compressor, which changes efficiency, but those are actually inefficient when you run them at maximum capacity, and they're twice the cost of a conventional system with our air conditioning. So what we've done in the past 5 years, we did this concept. We start going after competition, just in a clean energy track. Unlike, I'm a professor, this time instead of doing much in lab, we just did a prototype, and we went checked the business case. We won really 2 top business competitions. We teamed up with Department of Energy, and we just got a major grant from Department of Energy called Technology Commercial Fund. We brought on board Emerson and trained, and now we're building actually a full-scale prototype and testing in Department of Energy lab in Colorado. The goal here was we've proven the technology here to prove the economics. If it works, we're done. We're going to tell Emerson Train, go here, make it, because then it's OEM. And for me, this was, I did commercialization before. We tend to take things through the lab and try and build. In this case, we found that you're better off do the lab testing, prototype, go third-party national lab, let them validate it, do the economics, and bring strategic partners and say, look, if this works, you take it, we're done. Because the worst thing you want to do as a startup is start to building or reinventing the wheel. So we're on track. If this works out in the next 12 to 8 months, we're going to do field demo, and then we're done. We can license to them or we'll exit. Thank you very much. We'll happy to take questions.
We have time for several questions.
I will have to sing if you want to ask questions, so it's up to you.
So, maybe it's pretty early to answer the question, but how much will be the cost? And,
Yeah, no, actually that was the first thing we did. So the cost, there's 2 costs. One is the system integration, which is the battery controllers, and that's to the 5-ton units at about $1,500. So for 4 ton hour, that is actually cheap. That is about 200-300 ton hour, which is 4 kilowatt hours. So our goal was to be below $100 a kilowatt hour and equivalent to lithium battery, and always make it, because unlike batteries, this is not electrochemistry. This is physics, so it should last 15, 20 years. That was the first thing we tested before we did anything, that the economics have to pay off. You cannot, there's a lot of people, thank you, a lot of people who talk about technology and green. This is not. This is on economics, on its face value. It's cheap commodities, wax and graphite. Any other questions? Yes, sir.
And the applications, were we building efficiency, other sectors?
We're trying. The goal here was, what I saw that I'm in the energy storage. I run a company called Lithium Batteries Company also, and I was a professor of lithium batteries. But I found that the problem is with energy storage, we always look at one thing, either demand shift or ramping or ramping. The reality is you have to have flexible material to address that all, which means in this case, I can focus on efficiency and get it 10-15%, but I cannot compromise on cost because they will not buy it. So here the idea is I can shave the peak, not shift it. So I can just take the top by 2 kilowatt, that's the best dollar to dollar. I can improve the efficiency and I can cut the system size by 40%. And it was just that sweet spot that we did.
Question. So for an average home with annual 10,000 kilowatt hour usage, how much of that are you targeting, and then with that, what's the size of this thing?
Sure. So for homes, for regular homes, Today, there's no economic case because most residential are subsidized. But the only reason we'd be using home is, to your point, is efficiency. Right now, so that's how our approach has been more commercial, less technical in the beginning. We were not to prove anything. We're trying to see what is the first mover to the market, and it was commercial buildings. In commercial buildings, if I can cut peak, that is half of the bill. If I improve efficiency, they get credit. But by that time, then we start moving to secondary market. Residential, there will be regulations. Now, they're pushing regulation across the world. You have to improve by 10 to 20%. There aren't many technologies. This is a dinosaur technology, compressors and air conditioning. So in order to come up with something new, it's going to be very expensive. So this one actually is like the automotive industry. The hybrid solved quickly the problem fuel efficiency of CAFE by augmenting. We think this is going to be the next move for us, but that's going to be 10 years, which is for efficiency standards for buildings. But this is ready now. They did assessment. It's a problem just scaling up. And we think this can be in the market in 2-3 years top.